Somewhere in the universe right now, a star is dying in one of the most violent ways possible. It isn't exploding. It isn't collapsing. It's being pulled apart, atom by atom, by something it can't escape. A black hole. But here's what most people get wrong. The black hole doesn't just swallow the star whole. What actually happens is far stranger and far more terrifying. The star gets stretched like taffy, ripped into a long stream of superheated gas, and then whipped around the black hole at nearly the speed of light, releasing more energy in a few weeks than our sun will produce in its entire 10 billion year lifetime. It's called a tidal disruption event, and once you understand how it works, you'll never think about black holes the same way again. Before we get into this, if you find these kinds of deep explorations fascinating, a quick like or subscribe really helps the channel out. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Let's start with something you already know but probably haven't thought about very carefully. Gravity. You experience gravity every moment of every day. You feel it right now holding you to the surface of the earth. When you drop your phone, gravity pulls it to the floor. When you jump, gravity pulls you back down. It's the most familiar force in the universe. So familiar that you barely notice it. But gravity has a property that most people never think about. A property that, when taken to extremes, becomes one of the most destructive forces in the cosmos. And that property is this: gravity changes with distance. This sounds obvious when you say it out loud. Of course, gravity changes with distance. Things farther from Earth feel less gravity. Astronauts floating in the International Space Station experience less gravitational pull than people standing on the ground. The moon, even farther away, feels less pull from Earth than the space station does. The farther you get from a massive object, the weaker its gravitational pull becomes. Everyone knows this, but here's what most people miss. It's not just that gravity gets weaker with distance, it's how it gets weaker. Gravity doesn't decrease gradually and evenly like a dimmer switch being slowly turned down. It follows what physicists call an inverse square law. This means that if you double your distance from a massive object, the gravitational force doesn't just drop by half, it drops to 1/4. Triple your distance and gravity drops to 1/9. Move it 10 times farther away and gravity drops to 1/100th. This is important. It means gravity is extremely sensitive to distance. A small change in distance produces a disproportionately large change in gravitational force, and when you're close to a very massive object, this effect becomes extreme. Let me show you what I mean with something familiar. The ocean tides. You see the tides every day if you live near the coast. The water rises and falls in a rhythm that repeats roughly twice a day. Most people know that the moon causes the tides, but here's the part most people get wrong. The moon doesn't cause tides simply by pulling on the ocean. If the moon pulled on every part of the Earth equally, there would be no tides at all. The entire planet, water and rock together, would just move slightly toward the moon as one unified object. Nothing interesting would happen. Tides exist because the moon pulls on different parts of the Earth by different amounts. Think about it. The Earth has a diameter of about 7,926 miles. The side of the Earth facing the moon is roughly 4,000 miles closer to the moon than the center of the Earth, and the far side is roughly 4,000 miles farther away. The moon is about 238,855 miles away, so this 4,000-mile difference might seem insignificant. But because gravity changes with distance, the moon's pull on the near side of the Earth is measurably stronger than its pull on the center, and its pull on the center is measurably stronger than its pull on the far side. This difference in gravitational pull across the diameter of the Earth is what creates tides. The water on the side facing the moon gets pulled slightly more than the solid Earth beneath it, so it bulges outward toward the moon. And on the far side, the solid Earth gets pulled slightly more toward the moon than the water does, leaving the water to bulge outward in the opposite direction. That's why there are 2 high tides per day, one on the side of the Earth facing the moon, and one on the side facing away. This difference in gravitational pull across an extended object has a name. It's called a tidal force. And tidal forces are not unique to the Earth and Moon. They exist between any 2 objects where gravity varies across the size of one of them. They exist between Jupiter and its moons, between the Sun and every planet in the solar system, between binary stars orbiting each other, and between black holes and anything that comes too close. What makes tidal forces important is this: they don't just create gentle ocean tides. When tidal forces become strong enough, they can tear things apart. They can rip solid objects into fragments. They can shred entire worlds. And under the most extreme conditions, they can destroy stars. To understand why, let's think about what holds a star together in the first place. A star is a massive ball of gas, mostly hydrogen and helium, held together by its own gravity. Every particle in the star is gravitationally attracted to every other particle. This mutual gravitational attraction pulls the star inward, compressing it, trying to make it smaller. The only thing that prevents the star from collapsing under its own weight is the outward pressure generated by nuclear fusion in its core. The energy released by fusion pushes outward against the inward pull of gravity, and the 2 forces balance. This balance, called hydrostatic equilibrium, is what allows a star to exist as a stable, roughly spherical object for billions of years. But this balance can be disrupted. If something external applies a force that exceeds the star's own self-gravity, the star can't hold itself together anymore. It falls apart. And one of the most powerful external forces that can do this is the tidal force of a nearby black hole. Here's how it works. Imagine a star drifting through space, minding its own business, following a normal orbit around the center of its galaxy. Most stars do this their entire lives without incident. The center of most large galaxies contains a supermassive black hole, but most stars are far enough away that the black hole's gravity is negligible. The black hole is just sitting there in the center of the galaxy, and the star is orbiting thousands or tens of thousands of light years away, completely unaffected. But sometimes, through gravitational interactions with other stars, a star gets nudged onto a new orbit. Maybe a close encounter with a passing star changed its trajectory. Maybe a 3-body interaction in a dense stellar cluster kicked it inward. Whatever the cause, the star is now on an orbit that takes it much closer to the galactic center than it's ever been before. It's falling inward toward the supermassive black hole. Now, as the star approaches the black hole's gravitational pull gets stronger. But the key isn't just that the pull gets stronger, it's that the pull becomes increasingly uneven across the diameter of the star. Remember, gravity follows an inverse square law. The closer you get to a massive object, the more rapidly gravity changes over small distances, and a star, while small compared to the distances between stars, is not a point. It has a physical size. A star like our Sun has a diameter of about 864,000 miles. That's a significant extent. When the star is far from the black hole, the difference in gravitational pull between the near side and the far side of the star is tiny, negligible. The entire star feels essentially the same gravitational pull, and it just accelerates toward the black hole as a single, cohesive object. No distortion, no stretching, just motion. But as the star gets closer, the tidal forces grow. The near side of the star, the side facing the black hole, begins to feel a noticeably stronger pull than the far side. The difference is small at first. Maybe the near side feels a few percent more gravitational pull than the far side. The star's own self-gravity, the force holding it together, easily overwhelms this small difference. The star remains intact. Maybe it's slightly deformed, slightly elongated in the direction of the black hole, but it's essentially fine. As the star continues to approach, the tidal forces keep growing, and they grow rapidly because of that inverse square law. When the star is half as far from the black hole as before, the tidal force isn't just twice as strong, it's roughly 8 times stronger, because tidal forces follow an inverse cube law. They increase even faster with decreasing distance than gravity itself does. This is a critical point. Gravity drops off as the square of the distance, but the tidal force, the difference in gravity across an extended object, drops off as the cube of the distance. This means tidal forces are extremely distance sensitive. Far away, they're negligible. Close up, they're overwhelming. Let me explain why tidal forces follow an inverse cube law rather than an inverse square law. Gravity itself follows an inverse square law. At a distance d from a massive object, the gravitational acceleration is proportional to 1 over d squared. Now, the tidal force is the difference in gravitational acceleration across the star's diameter. If the star has a radius r, then the near side is at distance d minus r from the black hole, and the far side is at distance d plus r. The gravitational acceleration at the near side is proportional to 1 over the quantity d minus r squared, and at the far side, it's proportional to 1 over the quantity d plus r squared. The difference between these two values, when the star's radius is much smaller than the distance d, works out to be approximately proportional to r divided by d cubed. That's the inverse cube law. Tidal forces scale as 1 over d cubed. This means that when the star is at 100 times the critical distance, the tidal force is 1/millionth of the critical value. At 10 times the critical distance, it's 1,000th. At twice the critical distance, it's 1/8th. At the critical distance itself, the tidal force exactly matches the star's self-gravity, and at half the critical distance, the tidal force would be 8 times the star's self-gravity. This rapid increase is what makes tidal disruption events so sudden and so dramatic. For most of its approach, the star feels almost nothing. It's falling toward the black hole, accelerating, but structurally unaffected. The tidal forces are there, but they're far too weak to compete with the star's own gravity. The star doesn't know anything dangerous is happening, and then, in a relatively short span of time, the tidal forces ramp up explosively. The star goes from mildly deformed to catastrophically disrupted over a disturbingly short portion of its orbit. Now, let's talk about that critical distance. Astronomers call it the tidal radius. Some textbooks call it the Roche limit, though technically the Roche limit applies to bodies held together by gravity alone, like fluid bodies or rubble pile moons, while the tidal radius for stars also considers the internal structure of the star. But the concept is the same. It's the distance from the black hole at which the tidal force across the star exceeds the star's own self-gravity. Inside this radius, the star cannot hold itself together. Outside this radius, the star survives. The tidal radius depends on three things: the mass of the black hole, the mass of the star, and the radius of the star. More precisely, it depends on the ratio of the black hole's mass to the star's average density. A more massive black hole has a larger tidal radius. A denser star has a smaller tidal radius because denser stars are more tightly bound by their own gravity and harder to pull apart. The formula is elegant. The tidal radius is approximately equal to the radius of the star multiplied by the cube root of the ratio of the black hole's mass to the star's mass. If the black hole is 1,000,000 times more massive than the star, the tidal radius is about 100 times the star's radius. If the black hole is 1,000,000,000 times more massive than the star, the tidal radius is about 1,000 times the star's radius. For a star like our Sun approaching a supermassive black hole with a mass of about 1,000,000 times the Sun's mass, which is a relatively small supermassive black hole similar to some found in the centers of smaller galaxies, the tidal radius works out to be roughly 45 million miles. That's about half the distance from the Earth to the Sun, putting it somewhere between the orbits of Mercury and Venus. For context, if you replace the Sun with this black hole, a star passing within that boundary would be torn to pieces even though it was still tens of millions of miles away from the black hole itself. That might sound like a large distance, and by human standards it is, but by astronomical standards, it's incredibly small. 45 million miles is nothing compared to the distances between stars. It's a tiny target. The star has to pass very close to the black hole to be disrupted. This is why tidal disruption events are relatively rare. Stars don't stumble into the tidal radius very often. They have to be precisely deflected onto orbits that bring them dangerously close. Let me give you a sense of how unusual these orbits are. In a typical galaxy, the supermassive black hole at the center is surrounded by millions or billions of stars. But most of these stars are on stable orbits, thousands or tens of thousands of light years away. The gravitational sphere of influence of the black hole, the region where its gravity dominates over the combined gravity of the surrounding stars, extends only a few light years from the center. And the tidal radius is far smaller still. For a 1,000,000 solar mass black hole, the tidal radius is less than half an astronomical unit, which is roughly 4 light minutes. Compared to the overall scale of the galaxy, which might be 100,000 light years across, the tidal radius is absurdly tiny. It's like trying to hit a specific grain of sand on a beach by throwing a ball from a mile away. And yet, tidal disruption events do happen. Astronomers estimate that in a typical galaxy, a star is tidally disrupted roughly once every 10,000 to 100,000 years. That might sound rare, and for any single galaxy it is. But there are about 2 trillion galaxies in the observable universe. If each one produces a tidal disruption event every few tens of thousands of years, then across the entire observable universe, these events are happening constantly. Every few seconds, somewhere in the cosmos, a star is being ripped apart by a black hole. Let's go back to our star that's falling toward the black hole and trace what happens as it approaches the tidal radius. The star has been on its inward trajectory for a long time, perhaps thousands or millions of years, slowly approaching the galactic center. For most of this journey, nothing dramatic happens. The star is just falling, accelerating gradually as the black hole's gravity grows stronger. But the tidal forces are still negligible. The star looks and behaves like any normal star. As the star enters the final stages of its approach, things start to change. When it's at a distance of maybe 5 to 10 tidal radii from the black hole, the tidal forces begin to have a measurable effect. The star starts to deform. Its shape changes from a sphere to a slight ellipsoid, bulging toward the black hole on the near side and bulging away on the far side. Just like Earth's oceans bulge toward and away from the moon. But the deformation is small at this point. The star's self-gravity easily compensates. The star is still structurally intact, just slightly squished. At about 3 tidal radii, the deformation becomes more significant. The star is now noticeably elongated. If you could see it up close, it would look like an egg rather than a ball. The near side is being pulled harder than the far side, and the difference is becoming significant relative to the star's own binding gravity. The star is starting to strain. Internal pressures are shifting. The equilibrium between gravity and pressure is being disrupted. At about 2 tidal radii, the star is seriously deformed. It's now shaped more like a football than a sphere. The near side is bulging dramatically toward the black hole. Gas on the surface of the near side is starting to feel the black hole's gravity more strongly than the star's own gravity. The star is on the verge of losing material. Think of it like stretching a rubber band. At first, the rubber stretches easily and wants to snap back. But at some point, the stretch becomes too much, and the rubber starts to tear. The star is approaching that tearing point. And then, the star crosses the tidal radius. This is the point of no return for the star as a coherent object. Inside this radius, the tidal force exceeds the star's self-gravity. The star simply cannot hold itself together anymore. The gravitational force pulling the near side toward the black hole is stronger than the gravitational force trying to hold the star together. And the force pulling the far side away from the black hole, because it's being left behind as the near side accelerates faster, is also stronger than the star's binding gravity. The star begins to come apart. Not in an explosion, not in a sudden burst, but in a stretch. A long, agonizing stretch. The near side of the star accelerates faster because it's closer to the black hole and feels a stronger pull. The far side accelerates slower because it's farther away and feels a weaker pull. The middle of the star is caught between these two extremes. The result is that the star is stretched along the line connecting it to the black hole. It elongates dramatically, going from a football shape to a cigar shape to something more like a ribbon or a stream. This process has a name that has entered popular culture, though most people have only heard it in passing. Spaghettification. The term was popularized by Stephen Hawking in his book A Brief History of Time, and it describes exactly what it sounds like. The star is being stretched into a long, thin strand, like a piece of spaghetti. The name is playful, almost humorous, but the process itself is anything but. What's happening to the star is catastrophic. The temperatures, pressures, and forces involved are almost beyond calculation. And here is something crucial to understand. The star doesn't need to actually hit the black hole or cross the event horizon for this destruction to occur. The tidal radius for many supermassive black holes is well outside the event horizon. The star is torn apart in open space outside the point of no return. This is not a story about a star falling into a black hole and vanishing. This is a story about a star being destroyed before it ever reaches the black hole. The destruction happens in full view of the rest of the universe, and it produces an extraordinary amount of observable consequences that we'll explore as we continue. The tidal radius is an invisible boundary in space. There's no wall there, no barrier, no sign that says danger. There's just empty space, indistinguishable from the space around it. But cross that boundary with a star and the most fundamental structural integrity of a stellar object, the gravitational binding that has held it together for potentially billions of years, fails. The star that might have shone steadily for another 5 billion years is instead ripped into a thin filament of gas in a matter of hours. This is one of the most violent processes in astrophysics. Not because of an explosion, not because of a collision, but because of a gradient. A difference in the strength of gravity from one side of an object to the other. That's all a tidal force is. A gradient. And when that gradient becomes steep enough, when gravity changes sharply enough over a short distance, nothing can survive it. Not rock, not iron, not even the dense plasma of a stellar interior. The star doesn't go quietly either. As it's being pulled apart, the gas is compressed and heated by the intense forces. Different layers of the star are moving at different speeds, creating shearing forces that generate friction and turbulence. The gas heats up dramatically. What was once the interior of a star, gas at temperatures of millions of degrees, is now being stretched and shocked and heated even further. The disruption itself releases energy, not fusion energy, not chemical energy, gravitational energy. The potential energy stored in the star's position relative to the black hole is being converted into kinetic energy and heat as the gas falls inward and is stretched apart. And this is just the beginning. The star has been disrupted. It's been turned from a sphere of hot gas into a long, thin stream of debris. But the story is far from over. Because that debris doesn't just float there in space, it has to go somewhere. Some of it will fall toward the black hole, some of it will be flung outward. And what happens next? The collision of debris streams, the formation of a disk, the release of radiation creates one of the most luminous events in the known universe. But that comes later. For now, what matters is this. The star crossed an invisible line in space. A line defined entirely by the mathematics of gravity and the physical size and density of the star. And it was destroyed. Not by impact. Not by heat. Not by radiation. But by a gradient. By the simple fact that gravity on one side of the star was stronger than gravity on the other side, by an amount that exceeded what the star could withstand. That's the essence of a tidal disruption event. It's gravity at its most subtle and its most destructive simultaneously. A force so familiar that you feel it right now holding you in your chair. Applied in a way so extreme that it reduces a star to a thin river of glowing gas, spiraling around a point of infinite darkness. And every time it happens, every time a star crosses that invisible line, The universe lights up with a flare so bright that astronomers can see it from billions of light years away. A beacon of destruction that tells us something extraordinary just happened. A star met a black hole, crossed the tidal radius, and lost. So now we know the physics. We know what tidal forces are. We know why they grow so rapidly as the star approaches a black hole. We know about the tidal radius, that invisible boundary where the black hole's tidal force overwhelms the star's own gravity. But knowing the theory is one thing. Understanding what actually happens to the star, step by step, moment by moment, as it crosses that threshold, is something else entirely. Because the destruction of a star by a black hole is not a single event. It's a process. A drawn-out, violent, physically complex process that unfolds over hours, days, weeks, and ultimately months. And the details of that process are far more intricate and far more dramatic than most people imagine. Let's begin by setting the stage. Our star, a star roughly the size and mass of the Sun, has been falling toward the supermassive black hole at the center of its galaxy. This isn't a star that was minding its own business close to the black hole. It was originally on a perfectly safe orbit, thousands of light years from the galactic center. But at some point, maybe a few million years ago, a gravitational encounter with another star or a cluster of stars nudged it onto a new trajectory. This new orbit is highly elliptical, meaning it's extremely elongated. The star swings far out from the galactic center on one end of the orbit, and plunges deep toward the black hole on the other end. Think of a comet orbiting the Sun. Comets spend most of their time far from the Sun, moving slowly in the outer reaches of the solar system. But when they swing inward on the close approach, they move incredibly fast, whipping around the Sun before heading back out. Our doomed star is on a similar kind of orbit, except instead of the Sun at the center, there's a black hole with a mass of, say, a few million times the mass of the Sun. For most of this orbit, the star is far from the black hole, and nothing interesting happens. It's just a star moving through space. The black hole's tidal forces at that distance are completely negligible. The star is round, stable, burning hydrogen in its core, completely unaware that it's on a collision course with catastrophe. As the star begins its inward plunge, falling toward the closest point of its orbit, it accelerates. Gravity pulls it faster and faster. By the time it's approaching the tidal radius, it's moving at extraordinary speeds. For a supermassive black hole of a few million solar masses, a star approaching the tidal radius might be traveling at tens of thousands of kilometers per second. That's tens of millions of miles per hour. This is far faster than any spacecraft humans have ever built, far faster than any speed you can really comprehend. The star is hurtling toward the black hole like a bullet fired from a cosmic gun. And here's an important detail. The star's orbital speed matters because it determines how long the disruption takes. The star isn't hovering near the tidal radius, slowly being pulled apart over days. It's whipping past the black hole on a trajectory that takes it through the tidal radius in a matter of hours. The entire disruption, from the moment the star first crosses the tidal boundary to the moment it's been fully stretched into a stream of debris, happens astonishingly quickly. For a Sun-like star being disrupted by a black hole of a few million solar masses, the disruption timescale is roughly a few hours. Some calculations suggest as little as 2 to 3 hours. In the span of a single afternoon, a star that has existed for billions of years is reduced to a river of gas. Let's trace what happens during those hours. When the star first crosses the tidal radius, the disruption doesn't begin all at once. The tidal forces don't suddenly flip on like a switch. They've been building continuously during the approach. What changes at the tidal radius is that the forces now exceed the threshold that the star can withstand. But the star has internal structure. It's not a uniform ball of gas. It has layers with different densities and pressures. The outer layers of the star are less dense and more loosely bound than the core. So the outer layers begin to respond to the tidal forces first. The near side of the star, the side closest to the black hole, begins to stretch forward. Gas on the surface of the near side starts to accelerate away from the rest of the star, pulled toward the black hole. Simultaneously, the far side of the star begins to stretch backward. Gas on the far surface starts to lag behind the rest of the star, left behind as the center of mass accelerates forward. The star begins to elongate along the axis connecting it to the black hole. At this early stage, the elongation is visible, but the star still looks roughly like a cohesive object. It's an ellipsoid now rather than a sphere, like a ball of dough being stretched between two hands. But the internal pressure of the star is still fighting back. The hot gas is trying to maintain its spherical shape. Pressure gradients inside the star are pushing against the tidal distortion, trying to force the gas back into equilibrium. But the tidal forces are too strong. They're not just stronger than the star's self-gravity. They're increasing with every passing minute as the star continues to plunge deeper past the tidal radius. Remember, tidal forces scale as the inverse cube of distance. Every moment the star is closer to the black hole, and every moment the tidal forces are stronger. The star's internal pressure, which was already losing the battle at the tidal radius, falls further and further behind. The elongation accelerates. The star goes from an ellipsoid to something longer and thinner. Imagine squeezing a tube of toothpaste, except instead of toothpaste being pushed out of one end, the entire tube is being stretched in both directions. The near side is being pulled forward. The far side is being pulled backward. And the middle is being compressed laterally as the stretching squeezes the star thinner in the directions perpendicular to the stretch. This lateral compression is important. The star isn't just getting longer, it's getting narrower. The tidal forces are acting in 3 dimensions. Along the axis connecting the star to the black hole, the forces are stretching the star. But in the 2 directions perpendicular to that axis, the tidal forces are compressing the star. This is because the gravitational field of the black hole converges. Lines of gravitational force from a point mass converge toward the center. So gas on opposite sides of the star in the perpendicular directions is being squeezed together, pushed toward the axis of elongation. The net result is that the star is being stretched into a long, thin filament. Longer and longer, thinner and thinner. Within the first hour or so after crossing the tidal radius, the star has been transformed from a sphere roughly 864,000 miles across into an elongated structure that might be several million miles long, but only a few tens of thousands of miles wide. The transformation is dramatic and irreversible. At this point, the star has lost all resemblance to its former shape. It's no longer a star in any meaningful sense. It's a stream of gas. The core of the star, which is denser than the outer layers, resists disruption longer. The core's self-gravity is stronger because the material is more compact. While the outer layers are being stripped away and stretched into the growing filament, The core holds on for a while longer. But eventually, even the core succumbs. The tidal forces at this depth, past the tidal radius, are simply too powerful for any part of the star to withstand. The core stretches and breaks apart, its material joining the long stream of debris flowing around the black hole. By the time the star reaches the point of closest approach in its orbit, called the periapse or pericenter, the disruption is essentially complete. What was once a star is now a thin ribbon of hot gas, millions of miles long, curving along the trajectory of the original orbit. The gas is incredibly hot, heated by compression and shearing forces during the disruption process. Some of the gas has been heated well beyond the temperatures that existed in the star's original interior. The stretching and compression forces generated enormous amounts of friction and turbulence within the gas, converting kinetic energy into thermal energy. Now here's where things get really interesting, and this is the part that most popular descriptions of tidal disruption events completely skip over. When the star is destroyed, the debris doesn't all behave the same way. The fate of the gas depends critically on where it was located within the original star at the moment of disruption. Think about it this way. The near side of the star was closer to the black hole and was moving faster, pulled inward by the stronger gravitational force it experienced. The far side was farther from the black hole and was moving slower. The center of the star was somewhere in between. When the star comes apart, each piece of debris retains the velocity and position it had at the moment of disruption. And these differences in velocity and position lead to dramatically different orbital outcomes. The debris from the near side of the star, the material that was closest to the black hole, received a significant gravitational kick inward. It was accelerated to speeds higher than the center of mass of the star. This material ends up on tighter orbits around the black hole. These are bound orbits, meaning the debris doesn't have enough energy to escape the black hole's gravity. It will loop around the black hole and fall back toward the point where the disruption occurred. The debris from the far side of the star experienced the opposite effect. It was farther from the black hole, moving slower, and it received less gravitational acceleration during the disruption. In fact, some of this material ends up with enough velocity to escape the black hole's gravity entirely. It is flung outward on unbound trajectories, ejected into space at high speeds, never to return. And here's the remarkable result. Roughly half of the star's mass ends up bound to the black hole, destined to fall back and eventually be consumed. And roughly the other half of the star's mass is ejected from the system entirely, flung into the surrounding space at speeds of thousands or even tens of thousands of kilometers per second. Let me emphasize how extraordinary this is. The black hole doesn't consume the entire star. It gets only about half. The rest is thrown away. This might seem wasteful, but it's a natural consequence of the physics. The disruption happens at the tidal radius, which for many supermassive black holes is well outside the event horizon. The debris isn't inside the black hole's point of no return. Some of it has enough energy to leave. The gravitational interaction that shreds the star also slingshots half of the stellar material out into the galaxy at phenomenal speeds. This ejected material, this unbound debris, is itself an interesting phenomenon. It's hot gas, enriched with the chemical elements that were forged inside the star during its lifetime. Carbon, nitrogen, oxygen, heavier elements. This gas is ejected into the interstellar medium, the thin gas and dust that fills the space between stars. Over time, This ejected material mixes with the surrounding gas and might eventually be incorporated into new stars and planets. In a sense, the tidal disruption event recycles stellar material, returning it to the galactic ecosystem in a violent and dramatic fashion. But the real action is with the bound debris, the half of the star's mass that remains gravitationally bound to the black hole. This material doesn't just fall straight into the black hole. It can't. It has angular momentum, the rotational equivalent of regular momentum. The star was moving sideways as well as inward when it was disrupted, and that sideways motion means the debris follows curved orbital paths around the black hole. The bound debris loops outward after the disruption, reaches the farthest point of its new orbit, and then falls back toward the black hole. But here's the critical detail. Not all the bound debris falls back at the same time. Different pieces of debris have different orbital energies, which means they have different orbital periods. The most tightly bound material, the gas from the innermost part of the near side of the star, has the shortest orbital period. It loops around the black hole quickly and falls back toward the point of closest approach first. The less tightly bound material, from regions farther back in the star, has longer orbital periods and takes longer to fall back. The result is that the debris doesn't return all at once. It returns gradually, in a stream, over the course of weeks and months. Astronomers call this process fallback, and the rate at which the debris falls back follows a specific mathematical pattern. In the simplest theoretical models, the fallback rate, the amount of mass returning to the vicinity of the black hole per unit of time, follows a power law that decreases as time to the negative 5/3. This means the fallback rate is highest at the beginning, when the most tightly bound debris returns, and then decreases gradually over time as progressively less bound material trickles back. The timescale for this fallback depends on the properties of the black hole and the star. For a Sun-like star disrupted by a black hole of a few million solar masses, the most tightly bound debris has an orbital period of roughly a few weeks to a few months. This is the minimum fallback time. The first material returns to the vicinity of the black hole within weeks of the disruption. After that, the fallback continues for months, even years, as material on longer and longer orbits gradually returns. This extended fallback is why tidal disruption events aren't brief flashes. They're prolonged events that play out over months. The initial disruption itself takes only a few hours, but the consequences, the returning debris, the formation of a disk, the emission of radiation, unfold on much longer timescales. An astronomer observing a tidal disruption event doesn't see a sudden flash that appears and disappears. They see a gradual brightening that rises to a peak over weeks and then fades slowly over months. The entire event, from first detection to final fading, can last a year or more. Let's talk about the geometry of the debris stream, because this is genuinely beautiful in a terrifying way. When the star is disrupted, the debris is spread along the original orbital trajectory. But as the bound debris loops around the black hole and begins to fall back, it forms a long, thin stream that wraps around the black hole. Imagine a ribbon being pulled into a tight spiral. Each piece of the ribbon follows its own orbital path, but collectively they form a continuous stream that curves through space in an elongated elliptical arc. This stream is incredibly thin relative to its length. The width of the stream is determined by the original diameter of the star and the lateral compression during disruption. A stream that might be tens of millions of miles long could be only a few thousand miles wide. It's like a cosmic thread spiraling around a drain. And the stream isn't static. It's dynamic. The leading edge of the stream, the most tightly bound material, is already completing its first orbit and returning to the vicinity of the black hole, while the trailing edge, the least bound material, is still heading outward on the first leg of its much longer orbit. There's a continuous conveyor belt of gas, with material at different stages of its orbital journey all existing simultaneously in a complex three-dimensional structure around the black hole. When the leading edge of the fallback stream returns to the vicinity of the black hole, it encounters something that dramatically changes the evolution of the event. It runs into itself. The returning stream, coming back around the black hole from one direction, intersects with the outgoing stream of debris still heading away from the disruption point. This self-intersection of the debris stream is a pivotal moment in the evolution of a tidal disruption event. When two streams of gas moving at thousands of kilometers per second collide, the result is a violent shock. The kinetic energy of the colliding streams is converted into thermal energy. The gas heats up enormously. Temperatures at the intersection point can reach millions of degrees. The shocked gas radiates intensely, and this collision begins the process of dissipating the orbital energy of the debris, which is essential for the formation of an accretion structure around the black hole. Without this self-intersection, the debris would just keep orbiting indefinitely, looping around the black hole on elongated elliptical paths without ever settling into a compact disk. The self-intersection is what breaks the debris out of its original elongated orbits. The collision dissipates energy and angular momentum, causing the gas to settle onto tighter, more circular orbits closer to the black hole. Over time, through repeated collisions and dissipation, the gas settles into a more compact structure. Whether this structure is a classic thin accretion disk or something more complex is still a matter of active research and debate among astrophysicists. But the key point is that the self-intersection of the debris stream is the mechanism that converts a long, thin ribbon of gas into a concentrated structure that can feed the black hole. I want to pause here and emphasize something about the timescales involved, because this is often misunderstood. When people hear about a star being torn apart by a black hole, they tend to imagine it as a sudden, dramatic, almost instantaneous event. A star flies too close, gets ripped apart, boom, it's over. But that's not what happens. The actual disruption, the physical shredding of the star, does happen relatively quickly, in a matter of hours. But the disruption is just the beginning. The fallback of debris takes weeks. The self-intersection and formation of an accretion structure takes months. The resulting flare of radiation can last for a year or more. The entire event, from initial disruption to final fading, plays out on timescales that are long enough for astronomers to discover them, observe them, and study them in detail. This is actually one of the reasons tidal disruption events are so scientifically valuable. They're not over in a flash. They evolve slowly enough that astronomers can point telescopes at them and watch them unfold. Each event is a natural experiment, a controlled test of our understanding of gravity, fluid dynamics, accretion physics, and black hole behavior. By observing how the light from a tidal disruption event rises and falls over time, and by measuring the temperature and spectrum of the emitted radiation, astronomers can deduce the mass of the black hole, the type of star that was destroyed, the orbital parameters, and the physical processes occurring in the accretion flow. Another important detail about the debris stream is how fast the gas is moving. At the point of closest approach to the black hole, the debris is traveling at a significant fraction of the speed of light. For a black hole of a few million solar masses, the orbital speed at the tidal radius is roughly 10,000 to 30,000 kilometers per second. That's anywhere from 3% to 10% the speed of light. This is fast enough that relativistic effects begin to matter. Time dilation, gravitational redshift, the bending of light. The gas in the debris stream is moving through space-time that is measurably curved by the black hole's gravity, and the laws of Einstein's general relativity are needed to accurately describe its motion. The debris stream also precesses. In Newtonian gravity, a closed orbit traces out the same path over and over again. But in general relativity, orbits around massive objects precess. They rotate slowly, so each orbit traces out a slightly different path than the previous one. This precession means the debris stream doesn't come back to exactly the same point each orbit. The stream intersection point shifts, the geometry of the interaction changes, and the dynamics of the accretion flow become more complex. This precession is a direct effect of Einstein's theory of general relativity, and tidal disruption events are one of the few astrophysical settings where we can observe its effects on macroscopic streams of matter. Let me also address what happens to the star's magnetic field during disruption. Stars like the Sun have magnetic fields generated by the motion of conducting plasma in their interiors. When the star is torn apart, these magnetic fields are stretched and amplified along with the gas. The debris stream is threaded by magnetic field lines that were originally part of the star's internal magnetic structure. These fields can play an important role in the subsequent evolution of the accretion flow. They can generate turbulence, transport angular momentum, and even contribute to the launching of relativistic jets, narrow beams of matter and energy that shoot outward at nearly the speed of light from the vicinity of the black hole. Not all tidal disruption events produce jets, but when they do, the jets are among the most energetic phenomena in the universe. There's also the question of what happens to any planets that might have been orbiting the disrupted star. Stars often have planets, and those planets would have been accompanying the star on its fateful journey toward the black hole. The fate of these planets depends on their orbits and their distances from the star at the time of disruption. Planets close to the star would likely be disrupted as well, torn apart by the same tidal forces that destroyed the star. Planets farther out might survive the disruption of their parent star, but would find themselves suddenly orphaned, their gravitational anchor gone, left to drift through the galaxy as rogue planets. Some might be captured by the black hole's gravity and placed into new orbits. Others might be flung out of the galactic center at high speeds, ejected into intergalactic space. Imagine being on one of those planets if you could somehow survive the forces involved. You would see your sun, the star that had warmed your world for billions of years, begin to stretch and distort as it approached a point in the sky that appeared completely dark. Your sun would elongate, brighten, change color as its gas was heated and compressed. Within hours, your star would be gone, replaced by a luminous stream of glowing gas spiraling into darkness. and then you would be adrift, a planet without a star, falling through the gravitational landscape of the galactic center. The scenario is almost too dramatic for science fiction, and yet it almost certainly happens in reality across galaxies throughout the universe every time a star with planets is tidally disrupted. Now, let me pull all this together. A star on an unlucky orbit plunges toward a supermassive black hole. As it crosses the tidal radius, the difference in gravitational pull across its diameter overwhelms its own gravity. The star stretches, thins, and is drawn out into a filament of hot gas millions of miles long. This filament separates into two populations. Roughly half becomes bound to the black hole and begins to fall back over the following weeks and months. The other half is ejected into space at tremendous speeds, carrying stellar material into the galaxy. The bound debris forms a stream that wraps around the black hole, eventually intersecting with itself in a violent collision that heats the gas to millions of degrees and begins the formation of an accretion structure. The star is dead. It no longer exists as a coherent object. It has been converted into raw material, a stream of gas that will feed the black hole over the coming months. The energy released during this feeding process will produce a flare of light so intense that it can outshine the entire galaxy in which it occurs. But how that flare is produced, how the debris is actually consumed by the black hole, what kinds of radiation are emitted, and how astronomers on Earth detect these events from billions of light years away, that's what we need to explore next. Because what happens after the star dies is in many ways even more spectacular than the death itself. The star is gone. What existed for billions of years as a stable sphere of fusing hydrogen has been reduced to a long, thin ribbon of superheated gas curving through space around a supermassive black hole. Roughly half of the star's mass has been flung outward into the galaxy at thousands of kilometers per second, ejected on unbound trajectories, never to return. The other half remains gravitationally shackled to the black hole, stretched along elongated elliptical orbits, falling back toward the point of disruption in a drawn-out stream that will take weeks and months to fully return. But the destruction of the star is only the prologue. What happens next? What happens to that bound debris as it falls back and begins to interact with the black hole is where the real spectacle begins. Because the aftermath of a tidal disruption event produces one of the most energetic and luminous phenomena in the entire universe. A flare so bright that it can temporarily outshine every single star in the host galaxy combined. A flare visible from billions of light years away. And the physics that generates this flare is as fascinating as the disruption itself. Let's pick up where we left off. The most tightly bound debris, the gas that came from the near side of the star and was flung into the tightest orbits around the black hole, begins to fall back first. Its orbital period is the shortest, maybe a few weeks for a sun-like star disrupted by a black hole of a few million solar masses. This leading edge of the debris stream swings outward on its elliptical orbit, reaches the farthest point, slows, turns, and begins to fall back inward toward the black hole. As this gas returns, it's moving incredibly fast. Near the point of closest approach to the black hole, the debris is traveling at thousands of kilometers per second, sometimes reaching several percent of the speed of light. And it's compressed. The tidal forces that originally stretched the gas also squeezed it laterally, so the debris stream is thin, dense, and hot. It's a river of plasma flowing through curved space-time, at velocities that would be unimaginable in everyday experience. Now, here's where things get violent. As the leading edge of the debris stream completes its first orbit and returns to the vicinity of the black hole, it collides with the trailing portion of the stream, the gas that hasn't yet completed its first orbit and is still heading outward. This collision is called the stream self-intersection, and it's one of the most important moments in the entire tidal disruption event. Imagine two fire hoses pointed at each other from close range, each blasting water at thousands of miles per hour. When the two streams collide, the water doesn't just merge peacefully, it smashes together, sprays outward, and generates enormous pressure at the impact point. Now replace water with plasma moving at thousands of kilometers per second, and you begin to get a sense of what happens when the debris stream intersects itself. The collision generates a powerful shockwave. In the shock, the kinetic energy of the colliding streams is converted into thermal energy. The gas at the intersection point is heated to enormous temperatures, potentially tens of millions of degrees. This shocked gas radiates intensely, emitting light across a broad range of wavelengths. And the collision also serves a critical mechanical function. It dissipates the orbital energy of the debris. This energy dissipation is essential. Without it, the debris would just keep orbiting the black hole indefinitely on its original elongated elliptical orbits. The gas would swing in close, swing back out, swing in again, over and over, without ever settling into a compact structure near the black hole. For the black hole to actually consume the gas, something has to remove energy from the debris and cause it to spiral inward onto tighter and tighter orbits. The stream self-intersection is the first and arguably most important mechanism that begins this process. After the initial collision, the shocked gas begins to settle into a more compact configuration around the black hole. Exactly what this configuration looks like is still a matter of active research and vigorous debate among astrophysicists. In the simplest theoretical picture, the debris settles into a thin accretion disk, a flat, roughly circular structure of hot gas orbiting the black hole. The inner edge of the disk is close to the event horizon. The outer edge extends outward to wherever the debris has enough angular momentum to maintain a circular orbit. Gas in the disk slowly spirals inward, losing energy and angular momentum through viscous processes, until it eventually crosses the event horizon and falls into the black hole. But recent simulations and observations suggest the reality is more complex. The debris from a tidal disruption event might not form a clean, thin disk, at least not right away. The gas has a lot of angular momentum, and it arrives on highly elongated orbits with a wide range of energies. Converting this messy debris stream into a smooth, well-ordered accretion disk takes time. In the early phases, the accretion flow might be thick, puffy, and turbulent, more like a swollen torus of hot gas than a thin disk. Over time, as more debris falls back and more energy is dissipated through shocks and viscosity, the structure might evolve toward a thinner, more organized disk. But the transition can take months, and some events might never develop a fully thin disk at all. Regardless of the exact geometry, the fundamental physics is the same. Gas falls toward the black hole. As it spirals inward, it speeds up, it's compressed, and it heats up enormously. Let me explain why. When gas spirals inward toward a massive object, it converts gravitational potential energy into kinetic energy and heat. Think of water flowing down a drain. The water at the outer edge of the drain moves slowly. As it spirals inward, it speeds up. The same thing happens with gas spiraling toward a black hole, except the gravitational field is incomparably stronger. The gas near the inner edge of the accretion flow is moving at a significant fraction of the speed of light, and the temperatures are staggering. The primary heating mechanism in the accretion flow is friction, though in astrophysics we usually call it viscosity. Gas orbiting closer to the black hole moves faster than gas orbiting farther out, just as the inner planets of our solar system orbit the sun faster than the outer planets. When adjacent layers of gas are moving at different speeds, there's friction between them. This friction transfers angular momentum outward and energy inward. The result is that the inner gas loses angular momentum and spirals closer to the black hole, while the outer gas gains angular momentum and moves slightly outward. And the friction converts orbital energy into heat. In a traditional accretion disk, the source of this viscosity is thought to be turbulence generated by magnetic fields. The magnetorotational instability, first identified by astrophysicist Stephen Balbus and John Hawley in 1991, shows that even weak magnetic fields in a differentially rotating disk can generate turbulence that acts as an effective viscosity. This turbulence churns the gas, creates friction between layers, and drives the inward transport of matter and the outward transport of angular momentum. The temperatures generated by this process are extreme. In the inner regions of the accretion flow around a supermassive black hole, the gas can reach temperatures of tens of millions of degrees. At these temperatures, the gas is fully ionized. Electrons are stripped from their atoms, creating a plasma of free electrons and bare atomic nuclei. And this incredibly hot plasma radiates. It radiates a lot. The radiation produced by the accretion flow is what makes tidal disruption events visible from across the universe. The hot gas emits light across the entire electromagnetic spectrum, from radio waves to gamma rays. But the dominant emission depends on the temperature of the gas. Gas at tens of millions of degrees emits primarily in X-rays. Gas at hundreds of thousands of degrees emits primarily in ultraviolet and extreme ultraviolet. Gas at tens of thousands of degrees emits in optical light, the kind of light our eyes can see. In a typical tidal disruption event, the accretion flow has a range of temperatures. The innermost gas, closest to the black hole, is the hottest, emitting X-rays. Farther out, the gas is cooler, emitting ultraviolet light. Even farther out, at the edges of the accretion flow, the gas emits optical light. The overall spectrum of the event, the distribution of light across different wavelengths, reflects this temperature gradient. But here's something remarkable about tidal disruption events. The total amount of energy they release is absolutely enormous. When roughly half a solar mass of gas falls toward a supermassive black hole, the gravitational potential energy that's released is on the order of 10 to the power of 46 to 10 to the power of 47 joules. To put that in perspective, the sun produces about 3.8 times 10 to the power of 26 joules of energy every second. A tidal disruption event releases the equivalent of the sun's total energy output over millions to billions of years, compressed into a few months of intense radiation. The peak luminosity of a tidal disruption event can reach 10 to the power of 44 to 10 to the power of 45 earg per second, which is the standard unit astrophysicists use for luminosity. To put that in perspective, the total luminosity of the Milky Way the combined light of all 200 to 400 billion of its stars is roughly 10 to the power of 43 erg per second. A single tidal disruption event, one star being consumed by one black hole, can briefly produce 10 to 100 times more luminosity than our entire galaxy. It temporarily outshines every star in its host galaxy combined. Let that sink in for a moment. One star being torn apart by one black hole produces a flash of light brighter than hundreds of billions of stars shining together. This is the extraordinary efficiency of gravitational energy conversion. Nuclear fusion, the process that powers stars, converts about 0.7% of the rest mass energy of hydrogen into light. Gravitational accretion onto a black hole can convert up to roughly 6% of the rest mass energy of the infalling material into radiation for a non-spinning black hole, and up to about 42% for a maximally spinning black hole. That's roughly 10 to 60 times more efficient than nuclear fusion. Gravity is a far more powerful source of energy than nuclear reactions if you have a compact enough object to harvest it. Now, not all of this energy is released as visible light. Some of it goes into heating the gas to temperatures where it emits in wavelengths we can't see with our eyes, X-rays and extreme ultraviolet. Some of it goes into kinetic energy, driving outflows and winds from the accretion disk. Some of it might go into jets, and some of it is radiated away in directions we're not looking. But even the fraction that reaches our telescopes is enough to make tidal disruption events detectable from vast cosmic distances. Let's talk about what the light from a tidal disruption event actually looks like to astronomers on Earth. This is important because it's how we identify these events and distinguish them from other transient phenomena like supernovae and active galactic nuclei. A tidal disruption event appears as a sudden brightening at the center of a galaxy. Before the event, the galaxy looks normal, a collection of stars with a certain overall brightness. Then, over a period of weeks, a new source of light appears at the very center of the galaxy. This source brightens rapidly, reaching peak luminosity in roughly a few weeks to a couple of months. At peak, the central source can outshine the rest of the galaxy, and then it fades, slowly, over months and sometimes years. The light curve, the graph of brightness versus time, has a characteristic shape. A rapid rise followed by a gradual power law decline. This decline follows the predicted fallback rate of debris returning to the black hole. Remember, the rate at which bound debris falls back decreases as time to the negative 5/3 power. As less debris returns per unit time, less material is fed into the accretion flow, and less radiation is produced. The brightness drops accordingly. This characteristic decline rate, this time to the negative 5/3 power law, is one of the key signatures that astronomers use to identify tidal disruption events. But the light curve alone isn't enough. Supernovae also produce transient brightenings that rise and fall. So do active galactic nuclei, which can flare when a clump of gas falls into the black hole's existing accretion disk. To confirm that an event is truly a tidal disruption event, astronomers look at several additional properties. First, the location. Tidal disruption events occur at the exact center of a galaxy, where the supermassive black hole sits. Supernovae can occur anywhere in a galaxy, wherever there are stars. If a transient brightening is precisely coincident with the nucleus of the galaxy, that's a strong indication of a tidal disruption event. Second, the host galaxy. Tidal disruption events are most commonly found in galaxies that are otherwise quiet. galaxies that don't show signs of an active galactic nucleus. If a galaxy that has been quiescent for years or decades suddenly develops a bright nuclear flare, that's suspicious. Active galactic nuclei tend to show persistent, variable emission over years or decades. A tidal disruption event is a one-time event in a galaxy that was previously dark. Third, the spectrum. The light from a tidal disruption event has a distinctive spectrum. The thermal emission from the accretion flow produces a smooth, broad spectrum that peaks in the ultraviolet or soft X-ray range. There are also emission lines, specific wavelengths of light produced by certain ionized elements in the debris, hydrogen, helium, nitrogen, and others. The pattern and strength of these emission lines can distinguish a tidal disruption event from a supernova or an active galactic nucleus flare. Fourth, the temperature. Tidal disruption events tend to have remarkably constant temperatures during the declining phase. The peak temperature is typically a few tens of thousands of degrees, corresponding to emission in the ultraviolet. As the event fades, the luminosity drops, but the temperature stays roughly the same. This is different from supernovae, which typically cool as they fade. The constant temperature in tidal disruption events is thought to be related to the photosphere, the surface from which radiation escapes, which recedes as the accretion rate drops, keeping the temperature roughly steady even as the total luminosity declines. These multiple lines of evidence, location, host galaxy, light curve shape, spectral features, temperature evolution, allow astronomers to identify tidal disruption events with increasing confidence. And as our telescopes and surveys improve, we're finding more and more of them. Now, let's talk about one of the most dramatic features that some tidal disruption events produce: relativistic jets. A relativistic jet is a narrow beam of matter and energy launched from the vicinity of the black hole at speeds very close to the speed of light. Not all tidal disruption events produce jets. In fact, most don't. But the ones that do produce some of the most extreme phenomena in astrophysics. The first tidal disruption event clearly associated with a relativistic jet was Swift-J 164 4+57, detected in March 2011 by the Swift satellite. Initially, astronomers thought it was a gamma-ray burst, a completely different kind of event. But as they studied it more carefully, they realized it was coming from the center of a galaxy about 3.9 billion light-years away. The emission lasted much longer than a typical gamma-ray burst, and the properties of the radiation, its spectrum, its variability, its position at the exact center of the galaxy, were all consistent with the tidal disruption event that had launched a relativistic jet pointed almost directly at Earth. When a jet happens to be pointed in our direction, the radiation is dramatically amplified by a relativistic effect called beaming. The jet is moving toward us at nearly the speed of light, so the radiation is concentrated into a narrow cone aimed at our telescopes. This makes the event appear much brighter than it would if the jet were pointing in some other direction. Swift J1644 appeared to release more energy than a supernova, but that was partly an illusion caused by the beaming. The true energy output was lower, but still enormous. How do these jets form? The exact mechanism is still debated, but the leading theory involves magnetic fields. As the debris from the disrupted star falls toward the black hole and forms an accretion flow, magnetic fields in the gas are amplified by their rotation and compression. These amplified fields can thread through the spinning black hole itself, extracting rotational energy from the black hole and channeling it into two narrow beams of matter and energy that shoot outward along the black hole's rotation axis. This process, called the Blandford-Znajek mechanism, was first proposed in 1977 and is thought to power jets in active galactic nuclei as well. For the Blandford-Znajek mechanism to work efficiently, the black hole needs to be spinning rapidly. A non-spinning black hole can't power a jet through this mechanism. This means that the presence or absence of a jet in a tidal disruption event might tell us something about the spin of the black hole, a property that's otherwise extremely difficult to measure. If a tidal disruption event produces a powerful jet, it's a hint that the black hole is spinning rapidly. If it doesn't, the black hole might be slowly spinning or not spinning at all. Jets from tidal disruption events are rare, but scientifically invaluable. They give us a way to study jet formation and propagation in a relatively clean environment. In active galactic nuclei, jets have been operating for millions of years, and the environment around the black hole is complex and messy. In a tidal disruption event, the jet is newly launched, freshly formed from a well-defined source of material. The initial conditions are simpler and better understood. This makes tidal disruption event jets natural laboratories for studying one of the most poorly understood processes in astrophysics. Even when jets aren't formed, tidal disruption events often drive powerful outflows. These outflows are not as collimated as jets and don't move at relativistic speeds, but they're still fast, sometimes reaching speeds of 10,000 to 30,000 kilometers per second. These outflows are driven by the intense radiation from the accretion flow. When the luminosity of the accretion flow is high enough, the radiation pressure can actually push gas outward, driving a wind from the surface of the disk. This radiation-driven wind carries mass, energy, and momentum away from the accretion flow. These outflows have observable consequences. They can produce radio emission when they crash into the surrounding medium, the thin gas that exists around the galactic center. The outflowing material drives a shock into this ambient gas, heating it and accelerating electrons. These accelerated electrons spiral around magnetic field lines and emit radiation at radio wavelengths through a process called synchrotron emission. Radio telescopes can detect this emission, providing information about the speed and energy of the outflow and the density of the surrounding medium. Some tidal disruption events that are undetectable or faint in X-rays and optical light are quite bright in radio. This means that radio observations complement optical and X-ray observations, providing a more complete picture of the event. Different wavelengths probe different physical processes and different regions of the event. The optical emission comes from the outer parts of the accretion flow. The X-ray emission comes from the innermost regions near the event horizon. The radio emission comes from the outflows far from the black hole. Together, these observations paint a comprehensive portrait of the entire event, from the immediate vicinity of the black hole out to the surrounding galactic environment. Let me describe what a particularly well-studied tidal disruption event looks like across all these wavelengths. Consider a hypothetical event detected by a modern all-sky survey. First, the optical telescope detects a new source of light at the center of a previously quiet galaxy roughly 600 million light-years away. Over the next 3 weeks, the source brightens by a factor of roughly 100, reaching a peak optical luminosity several hundred times the luminosity of the sun. No, several billion times the luminosity of the sun. The color of the source is blue, indicating a temperature of roughly 30,000 to 50,000 degrees. Simultaneously, an ultraviolet telescope detects even brighter emission from the same source. The peak of the emission is in the ultraviolet, consistent with a thermal source at tens of thousands of degrees. This ultraviolet dominance is characteristic of tidal disruption events and distinguishes them from supernovae, which tend to peak at redder wavelengths. An X-ray telescope also detects emission from the source, though it's fainter than the ultraviolet emission. The X-rays come from the hottest innermost regions of the accretion flow, where temperatures reach millions of degrees. The X-ray emission varies rapidly, on timescales of hours to days, reflecting the turbulent conditions in the inner accretion flow. Weeks later, a radio telescope detects faint radio emission from the same location. This emission grows slowly over months, as the outflow from the event expands outward and interacts with the surrounding medium. The radio emission provides a calorimeter for the total energy in the outflow, allowing astronomers to estimate how much energy was injected into the surroundings by the event. Spectroscopic observations reveal broad emission lines of hydrogen and helium in the optical spectrum. These lines are Doppler broadened, meaning they're smeared out by the motion of the emitting gas. The width of the lines indicates gas velocities of 10,000 to 20,000 kilometers per second, consistent with material orbiting or falling toward a supermassive black hole. From the line widths and the luminosity of the event, astronomers estimate the mass of the black hole to be a few million solar masses. Over the following months, the event fades. The optical and ultraviolet luminosity declines following the predicted time to the negative 5/3 power law. The X-ray emission fades as well, though with more variability. The radio emission continues to grow for a while as the outflow expands, then eventually peaks and begins to fade as the outflow decelerates. A year after the initial detection, the event has faded to a fraction of its peak brightness. 2 years later, it's barely detectable. The galaxy has returned to its quiescent state, as if nothing happened. But the black hole at its center is slightly more massive than before, having consumed roughly half a solar mass of stellar material. This is the life cycle of a tidal disruption event as seen from Earth. A sudden brightening, a peak, a gradual decline, and eventually a return to normalcy. The entire event, from first detection to final fading, can last 1 to 2 years. But in that time, more energy is released than the Sun will produce in its entire 10 billion year lifetime. More energy than a billion suns produce in a year. All from the gravitational destruction of a single star. These events are among the most luminous transient phenomena in the universe. Only gamma-ray bursts and certain types of superluminous supernovae can rival them in peak brightness. And unlike gamma-ray bursts, which last seconds to minutes, tidal disruption events last months, giving astronomers plenty of time to observe and study them in detail. The energy source is gravity. Pure gravitational potential energy, converted into radiation through the accretion process. The star's mass falls toward the black hole, accelerates, heats up through friction and shocks, and radiates. It's the same process that powers quasars and active galactic nuclei. But in a tidal disruption event, we see it happening in real time, from start to finish, with a known fuel source, one disrupted star. This makes tidal disruption events uniquely valuable as laboratories for studying accretion physics. We know what went in, roughly 1 solar mass of gas. We can measure what comes out, the radiation across all wavelengths. And from the relationship between input and output, we can deduce the efficiency of the accretion process, the geometry of the accretion flow, and the physics of radiation generation near a black hole. There's also the matter of what the accretion process does to the material before it enters the black hole. Not all the gas that falls back reaches the event horizon. Some of it is blown away by radiation pressure. Some of it is ejected in outflows and winds. Some of it is launched in jets if conditions are right. The fraction that actually crosses the event horizon and adds to the black hole's mass is called the accretion efficiency. For a standard thin disk around a non-spinning black hole, the radiative efficiency is about 6%. For a rapidly spinning black hole, it can be much higher. And in the early phases of a tidal disruption event, when the fallback rate is very high, the accretion rate can exceed a critical value called the Eddington limit. The Eddington limit is the maximum luminosity at which the outward radiation pressure balances the inward gravitational force. Above this limit, radiation pressure drives gas outward rather than letting it fall in. When the accretion rate exceeds the Eddington limit, the accretion flow becomes super Eddington. The radiation is partially trapped within the infalling gas, unable to escape efficiently. The flow becomes thick and puffy, quite different from a thin disk. Powerful winds are driven from the surface of the flow, carrying mass and energy outward. Many tidal disruption events are thought to be super Eddington, especially in their early phases when the fallback rate is highest. This means the standard thin disk model doesn't fully apply, and more complex models are needed to describe the accretion flow. The super Eddington phase is when the event is at its brightest, when the most dramatic outflows are launched, and when the physics is most complex and least understood. Understanding super Eddington accretion is important far beyond tidal disruption events. It's thought to play a crucial role in the growth of supermassive black holes in the early universe. The first supermassive black holes grew to billions of solar masses within the first billion years after the Big Bang, which is puzzling because standard Eddington limited accretion would have taken much longer. Super Eddington accretion, where the black hole feeds faster than the Eddington limit would normally allow, might be the answer. Tidal disruption events give us a front row seat to super Eddington accretion in action, allowing us to study a process that shaped the growth of black holes across cosmic history. Every tidal disruption event is a story written in light, a story that begins with a star on a doomed orbit, passes through the violence of tidal disruption and the chaos of debris stream collision, and culminates in a months-long outpouring of radiation so intense that it can be seen from the other side of the observable universe. The light carries information. It tells us the mass of the black hole. It tells us the type of star that was destroyed. It tells us the efficiency of accretion, the strength of magnetic fields, the speed of outflows, and the geometry of the accretion flow. It tells us things about black holes that we simply cannot learn any other way. And the light is still out there. Every tidal disruption event that has ever occurred in any galaxy at any time in cosmic history produced radiation that is still traveling through space. The flare from a tidal disruption event that happened a billion years ago in a distant galaxy is still propagating, spreading outward at the speed of light, dimming with distance, but never quite disappearing. If our telescopes are pointed in the right direction at the right time, we can catch it. We can hear the story it carries. We can learn about a black hole and a star that interacted 1 billion years ago in a galaxy we've never even named. That is the power and the beauty of tidal disruption events. They're not just violent cataclysms, they're messages, cosmic telegrams written in photons, sent across the universe by the most extreme physics imaginable, carrying information about the dark hearts of galaxies to anyone with the instruments and knowledge to decode them. So now we understand what happens when a star is torn apart. We understand the physics of tidal forces, the step-by-step destruction of the star, the formation of the debris stream, and the violent accretion process that produces one of the most luminous events in the universe. But there's a crucial piece of this story that we haven't addressed yet, and it changes everything about how we think about tidal disruption events and about black holes themselves. Not every black hole destroys stars the same way. In fact, some black holes don't produce visible tidal disruption events at all. They swallow stars whole, silently, without any fanfare, without any flash of light, without any detectable signal of any kind. The star simply disappears. And whether a black hole produces a spectacular, observable tidal disruption event, or quietly consumes a star in darkness, depends on one single factor: the mass of the black hole. This might seem counterintuitive at first. You might think a more massive black hole would produce a more dramatic tidal disruption event. Bigger black hole, bigger explosion, bigger flare. But the physics actually works the other way around. And understanding why requires us to think carefully about two distances: the tidal radius and the event horizon. We've already discussed the tidal radius in detail. It's the distance from the black hole at which the tidal forces exceed the star's self-gravity. Inside this radius, the star is torn apart. Outside it, the star survives. The tidal radius depends on the mass of the black hole and the size and density of the star. For a Sun-like star, the tidal radius scales with the cube root of the black hole's mass. So if the black hole is 1 million times the mass of the Sun, the tidal radius is about 100 solar radii from the center. If the black hole is 1 billion times the mass of the Sun, the tidal radius is about 1,000 solar radii. Now let's think about the event horizon. The event horizon is the boundary around a black hole beyond which nothing can escape. Not light, not matter, not information of any kind. Once something crosses the event horizon, it's gone. It's inside the black hole forever. For a non-rotating black hole, the event horizon is called the Schwarzschild radius, and it scales linearly with the black hole's mass. Double the mass, double the Schwarzschild radius. A black hole with a mass of 1 million solar masses has a Schwarzschild radius of about 3 million kilometers. A black hole with a mass of 1 billion solar masses has a Schwarzschild radius of about 3 billion kilometers, which is roughly the distance from the Sun to Uranus. Here's the critical point. The tidal radius scales with the cube root of the black hole's mass. The event horizon scales linearly with the black hole's mass. Linear growth is much faster than cube root growth. This means that as the black hole gets more massive, the event horizon grows faster than the tidal radius. For small supermassive black holes, the tidal radius is well outside the event horizon. The star is torn apart in open space, far from the point of no return, and the resulting debris produces a brilliant flare. But as the black hole's mass increases, the event horizon catches up to the tidal radius. And at a certain critical mass, the event horizon actually overtakes the tidal radius. When this happens, the implications are profound. If the event horizon is larger than the tidal radius, then the star crosses the event horizon before the tidal forces become strong enough to tear it apart. The star enters the black hole intact. It's swallowed whole, no disruption, no debris stream, no accretion disk, no flare, no radiation, nothing. The star simply vanishes behind the event horizon, and the outside universe never knows it happened. For a star like the Sun, this critical black hole mass is roughly 100 million solar masses. That's the dividing line. Below about 100 million solar masses, the tidal radius is outside the event horizon, and the black hole can produce visible tidal disruption events. Above about 100 million solar masses, the event horizon swallows the star before tidal forces can do their work. The star is consumed whole, invisibly, silently. Let me put some numbers on this to make it concrete. Consider a black hole with a mass of 1 million solar masses. This is a relatively small supermassive black hole, similar to the one at the center of a modest galaxy. For a Sun-like star, the tidal radius is about 70 million kilometers from the center, roughly half the distance from the Earth to the Sun. The Schwarzschild radius of this black hole is about 3 million kilometers. So the tidal radius is more than 20 times larger than the event horizon. The star is torn apart far from the event horizon. The debris has plenty of space to form a disk and produce radiation. This is the classic tidal disruption event, the kind that astronomers observe. Now consider a black hole with a mass of 10 million solar masses. The tidal radius for a Sun-like star is now about 150 million kilometers, roughly the distance from the Earth to the Sun. The Schwarzschild radius has grown to about 30 million kilometers. The tidal radius is still about 5 times larger than the event horizon. The star is still disrupted outside the event horizon. There's still room for a visible flare, but the ratio is shrinking. At 50 million solar masses, the Schwarzschild radius is about 150 million kilometers. The tidal radius for a Sun-like star is roughly 250 million kilometers. The ratio is now less than 2 to 1. The star is just barely disrupted outside the event horizon. Some of the debris falls directly into the black hole rather than forming a long-lived accretion disk. The event might be less luminous and harder to detect. At 100 million solar masses, the Schwarzschild radius is about 300 million kilometers. The tidal radius is roughly 320 million kilometers. The two distances are nearly equal. The star crosses the event horizon almost immediately after being disrupted. Much of the debris falls directly in. The flare, if there is one, is muted, brief, and dim compared to disruptions around smaller black holes. And at 1 billion solar masses, the Schwarzschild radius is about 3 billion kilometers. The tidal radius for a Sun-like star is only about 700 million kilometers. The event horizon is more than 4 times larger than the tidal radius. The star enters the event horizon completely intact, with the tidal forces still well below the threshold needed for disruption. The star is swallowed whole. No disruption occurs. No signal is emitted. The black hole gains mass, but the universe outside sees nothing. This is one of the most striking results in the physics of tidal disruption events. The most massive black holes in the universe, the ones at the centers of the largest galaxies, the ones that contain billions or even tens of billions of solar masses. cannot produce visible tidal disruption events for ordinary stars. They eat stars silently. The star falls through the event horizon. It crosses the point of no return and is gone. No light escapes. No radiation is produced outside the horizon. No astronomer anywhere in the universe could ever know it happened. Think about what this means. The supermassive black hole at the center of M87, the galaxy whose black hole was famously imaged by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion solar masses. Its event horizon has a diameter larger than the orbit of Pluto. A sun-like star falling into this black hole would be swallowed whole without producing any detectable signal. The tidal forces at the event horizon would be surprisingly gentle. In fact, for an astronaut falling into a black hole this massive, the tidal forces at the event horizon would be weaker than the tidal forces you experience right now, sitting on the surface of the Earth due to the moon's gravity. You cross the event horizon without feeling anything unusual. You wouldn't be spaghettified. You wouldn't be torn apart. You just pass through, and from the outside universe's perspective, you'd be gone forever. This is deeply counterintuitive. We associate black holes with extreme destruction, with spaghettification, with violent tidal forces. And those things are real, but they happen near smaller black holes. The largest black holes are actually gentler at their event horizons. Their tidal forces at the horizon are weaker precisely because the horizon is so far from the singularity. The destructive tidal forces still exist, but they're encountered deep inside the event horizon, well past the point of no return, where no information can escape. Now, this critical mass of about 100 million solar masses applies specifically to sun-like stars. Stars with different sizes and densities have different critical masses. A red giant star, which is much larger and less dense than the Sun, is more easily disrupted by tidal forces. Its tidal radius is larger relative to the event horizon. This means that even very massive black holes might still be able to disrupt red giants. A black hole of 1 billion solar masses might swallow a sun-like star whole, but could still tidally disrupt a red giant because the red giant's larger size gives the tidal forces more to work with. Conversely, a white dwarf, which is much smaller and much denser than the Sun, is very difficult to disrupt. White dwarfs are so compact that only black holes of relatively low mass, around 1,000 to 100,000 solar masses, intermediate mass black holes, have tidal radii outside the event horizon for these dense stellar remnants. A supermassive black hole of 1 million solar masses would swallow a white dwarf whole, just as a 1 billion solar mass black hole would swallow a sun-like star. The white dwarf is simply too dense. Its self-gravity is too strong. The black hole would need to get so close to overcome that self-gravity that the star would already be inside the event horizon. This size and density dependence creates a fascinating landscape of tidal disruption possibilities across the universe. Small supermassive black holes disrupt ordinary stars. Intermediate mass black holes might disrupt white dwarfs. The largest supermassive black holes can only disrupt the fluffiest, most extended stars like giants and supergiants. Each combination of black hole mass and stellar type produces a different kind of event with different timescales, different luminosities, and different observable signatures. This brings us to one of the most important scientific contributions of tidal disruption events. They reveal black holes that would otherwise be invisible. Most supermassive black holes in the universe are dormant. They're not actively consuming large amounts of material. They're not powering bright, active galactic nuclei or quasars. They're just sitting there in the centers of their galaxies, invisible, betrayed only by their gravitational effects on nearby stars. We know the black hole at the center of the Milky Way, Sagittarius, a star, has a mass of about 4 million solar masses. But we know this not because we can see the black hole itself, but because we can track the orbits of stars near the galactic center and infer the mass of the unseen object they're orbiting. But we can't track individual stellar orbits in distant galaxies. The stars are too faint and too close together to resolve individually. So how do we know there are supermassive black holes in those galaxies? For active galaxies, the black hole reveals itself through the radiation produced by its accretion disk. But for dormant galaxies, galaxies where the black hole isn't actively feeding, there's often no direct evidence for the black hole's existence. Tidal disruption events change this. When a star is disrupted by a dormant black hole, the resulting flare lights up the galactic center like a lighthouse. A galaxy that was previously quiet and unremarkable suddenly brightens dramatically in its core. Astronomers detect this brightening and recognize it as a tidal disruption event based on its characteristic light curve, the way it rises and fades over time, and its spectral properties. From the properties of the flare, they can estimate the mass of the black hole and confirm its existence. This means that tidal disruption events serve as cosmic probes, illuminating black holes that we couldn't otherwise detect. Every tidal disruption event we observe tells us there's a supermassive black hole at the center of that galaxy. And since tidal disruption events can be seen from billions of light years away, they allow us to study black holes in very distant galaxies that are too far away for any other method of black hole detection to work. As of the mid-2020s, astronomers have detected roughly 100 confirmed tidal disruption events, with the number growing rapidly as new survey telescopes come online. The first convincing tidal disruption event candidates were identified in the 1990s by the Rosette X-ray satellite, which detected unusual X-ray flares from the centers of otherwise quiet galaxies. These flares had the right properties: a rapid rise followed by a gradual decline following approximately the predicted time to the negative 5/3 power law, to be consistent with the fallback of debris from a tidally disrupted star. Since then, our ability to detect tidal disruption events has improved dramatically. Optical surveys like the Zwicky Transient Facility and the All-Sky Automated Survey for Supernovae scan the entire visible sky every few nights, looking for transient events, things that brighten and fade. These surveys have discovered dozens of tidal disruption events in optical light. X-ray telescopes continue to find events that are brightest in X-rays. Radio telescopes have detected the jets and outflows associated with some events. And ultraviolet observatories have captured the peak emission from the hottest parts of the accretion flow. Each new detection adds to our understanding. We're learning that tidal disruption events are more diverse than early theoretical models predicted. Some events are bright in X-rays but faint in optical light. Others are bright in optical and ultraviolet but show very little X-ray emission. Some events produce powerful relativistic jets. Most do not. Some events rise to peak brightness in just a few weeks. Others take months. Some fade rapidly. Others linger for years. This diversity is telling us that the physics of tidal disruption events is more complex than simple models suggest. The interplay between the debris stream dynamics, the self-intersection geometry, the magnetic field amplification, the formation of the accretion flow, and the possible launching of jets creates a rich variety of outcomes that depend on the specific properties of each event, the mass and spin of the black hole, the type of star, the orbital trajectory, the angle at which we observe the event. The future of tidal disruption event research is extraordinarily promising. The Vera C. Rubin Observatory, expected to begin full operations in the mid-2020s, will survey the entire southern sky every few nights with unprecedented depth and coverage. It's expected to detect thousands of tidal disruption events over its 10-year survey. This will increase our sample size by a factor of 10 or more, allowing statistical studies that are impossible with the current small sample. We'll be able to measure the rate of tidal disruption events as a function of galaxy type, black hole mass, and redshift. We'll be able to identify rare subtypes of events that occur too infrequently to be found in current surveys. Future X-ray missions will also transform the field. The Einstein probe, launched in 2024, is specifically designed to detect transient X-ray sources, including tidal disruption events. It can survey large areas of the sky in X-rays, catching events in their early stages when the X-ray emission is rising, and gravitational wave detectors might eventually detect tidal disruption events through an entirely different channel. The disruption of a star by a supermassive black hole produces gravitational waves, ripples in space-time itself. These gravitational waves are too weak and at too low a frequency for current detectors like LIGO to detect. But future space-based gravitational wave observatories like LISA, the Laser Interferometer Space Antenna, will be sensitive to gravitational waves at precisely the frequencies produced by tidal disruption events. LISA could potentially detect the gravitational wave signal from a star being torn apart, providing a completely independent measurement of the black hole's mass and the dynamics of the disruption. Imagine combining observations of the same event across the electromagnetic spectrum: optical light, ultraviolet, X-rays, radio waves, and gravitational waves. Each type of observation probes different physical processes and different regions of the event. Optical and ultraviolet light tell us about the temperature and extent of the radiating gas. X-rays probe the innermost accretion flow close to the event horizon. Radio waves reveal jets and outflows. Gravitational waves measure the mass and spin of the black hole directly, without any assumptions about the electromagnetic emission. Together, these observations would give us an extraordinarily detailed picture of the disruption process, testing our theories of gravity, accretion, and black hole physics with unprecedented precision. Tidal disruption events also teach us something profound about the nature of galaxies themselves. We tend to think of galaxies as peaceful collections of stars, gas and dust, slowly orbiting their common center of mass. And most of the time, that's an accurate picture. But at the very center, within a few light years of the supermassive black hole, galaxies are not peaceful at all. They're dynamic, chaotic environments where stars jostle for orbital space, where gravitational encounters can fling stars onto dangerous trajectories, and where every few tens of thousands of years, one of those stars meets its end in a violent encounter with the black hole. The rate of tidal disruption events tells us about the dynamics of these central regions. In galaxies where the stellar density near the center is high, where stars are packed closely together, gravitational encounters are more frequent, and stars are more likely to be deflected onto orbits that take them close to the black hole. These galaxies should have higher tidal disruption rates. In galaxies with lower central stellar densities, events should be rarer. Observations broadly confirm this. Tidal disruption events are more common in certain types of galaxies, particularly in post-starburst galaxies, also called E+A galaxies. These are galaxies that recently underwent a burst of star formation but have since quieted down. They tend to have high central stellar densities, which increases the rate of gravitational encounters that can funnel stars toward the black hole. The rate of tidal disruption events in these galaxies is estimated to be 10 to 100 times higher than in typical quiescent galaxies. Understanding these rates helps us understand how supermassive black holes grow. Over cosmic time, tidal disruption events contribute to the mass of the black hole. Each event delivers roughly half a solar mass to the black hole. If events happen every 10,000 to 100,000 years, the black hole gains one solar mass every 20,000 to 200,000 years. Over billions of years, this can add up to millions of solar masses, but probably not enough to build the most massive black holes from scratch. Tidal disruption events are a secondary feeding mechanism, supplementing the much larger amounts of gas that fall into black holes during periods of active accretion, such as when the black hole powers a quasar. But tidal disruption events are special because they happen even when the black hole is dormant, when there's no other gas falling in, when the galaxy is quiet. They're the background hum of black hole feeding, a slow, steady trickle of stellar debris that keeps the black hole growing even during its quietest periods. There's also something philosophically striking about tidal disruption events. They represent a direct confrontation between two of the most fundamental forces in astrophysics: the gravity that holds a star together and the gravity that tears it apart. The star's self-gravity, the force that compressed a cloud of hydrogen into a nuclear furnace and maintained it for billions of years, meets the tidal gravity of the black hole, a force generated by the most extreme concentration of mass in the universe. And the tidal gravity wins. The star, an object that might have burned steadily for another 5 or 10 billion years, is destroyed in hours. Billions of years of stable existence undone by a single close encounter. Every tidal disruption event is a reminder of the violence that lurks at the heart of every galaxy. The centers of galaxies are not empty. They contain objects of almost incomprehensible gravitational power, objects that can tear apart the fundamental building blocks of the cosmos with nothing more than the gradient of their gravitational field. These black holes are patient. They sit at the centers of their galaxies for billions of years, waiting. And every so often, the random walk of stellar orbit sends a star too close. The star crosses that invisible boundary, the tidal radius, and in hours it's converted from a stable, luminous sphere into a thin stream of gas, spiraling toward an object from which nothing returns. Somewhere in the universe right now, this is happening. Somewhere, a star that has been shining for billions of years is approaching a point of no return. Its outer layers are beginning to stretch. The far side is starting to lag behind. The gas is heating, the shape is distorting, and within a few hours, that star will no longer exist. It will be a memory written in light, a flare that will travel across billions of light years of space, dimming with distance but never fully disappearing, carrying the story of a star's final moments to anyone with a telescope pointed in the right direction. And somewhere in another galaxy, the same thing is happening around a black hole so massive that no flare is produced at all. The star falls through the event horizon intact, whole, undamaged by tidal forces, and simply ceases to exist as far as the outside universe is concerned. No light, no signal, no evidence, just a black hole that's slightly more massive than it was a moment ago, and a star that has vanished from the universe as completely as if it had never existed. The universe is full of these silent meals. The largest black holes consume stars the way a whale consumes plankton, effortlessly, continuously, and invisibly. We'll never know how many stars have been lost this way. The information is locked behind event horizons, forever inaccessible. But the tidal disruption events we can see, the ones that happen around smaller supermassive black holes, the ones that produce those brilliant flares of radiation, those are gifts. They're windows into physics that we can't study any other way. They show us how matter behaves under the most extreme gravitational conditions outside of a black hole merger. They reveal dormant black holes hiding in the centers of quiet galaxies. They test our theories of general relativity, accretion physics, and the dynamics of stellar systems. And they remind us, every time one is detected, that the universe is not a calm, static place. It's dynamic, violent, and full of events that dwarf anything in human experience. The next time you look at a galaxy in a photograph, a beautiful spiral or a smooth elliptical, remember what's at the center. There's a black hole there. It might be quiet right now. It might not have consumed a star in thousands of years, but it's there, waiting. And one day, another star will wander too close. It will cross the tidal radius, and in a few hours it will be gone, converted into a stream of superheated gas that will light up the galaxy with a flare visible from across the observable universe. That's what really happens when a black hole tears a star apart. Not a simple swallowing, not a quiet disappearance, but a drawn-out, physically precise step-by-step destruction that begins with an invisible line in space, proceeds through the most violent stretching forces in nature, and ends with either a beacon of light that outshines 100 billion stars, or a silent consumption behind an event horizon from which no information returns. Both outcomes are happening right now, across the universe, in galaxies we can see, and galaxies we can't. Stars are dying in ways most people never imagine. And every one of those deaths tells us something about the universe we live in, about the nature of gravity, about the structure of space-time, and about the extraordinary, terrifying, beautiful physics that governs the cosmos at its most extreme.